In this video, we're going to discuss the multivariable chain rule. So let's flash back to the single variable chain rule from our first calculus course. So imagine we had a situation where the variable y depends on x and the variable x depends on t. So in first year calculus course, we would ask something like calculate dy by dt. Let's say we want to figure out how y is changing over time, or the rate of change of y with respect to time. And we learned in our first calculus course that to get dy by dt, we're going to take dy by dx, and we're going to multiply that by dx by dt. So that's our single variable chain rule from our first calculus course. So we're now going to extend that to situations where we have more variables coming into play. Let's try an example. So it's going to be really common when you have multiple variables to draw a diagram to express the relationship between the variables. So imagine that you have a variable w, and it depends on x and y. And x and y each depend on two other variables. Let's call them u and v. So the diagram showing the relationship to the variables is there. Okay, now based on this diagram, let's say we want to find the partial derivative of w with respect to v. So delta w over delta v. Want to figure out how w is changing with respect to the variable v. So the idea for how we approach this is we're going to look at all the paths in the diagram that start at w and end at v. So there are going to be two different paths. One way to do it is to travel along this path here. Another way to do it is to travel along that path there. So we're going to say partial derivative of w with respect to v. Well, it's going to have two terms in the sum representing the two different paths. And along each of the path, we're just going to do a similar kind of process as we did with the single variable chain rule. So we'd say we need to multiply partial derivative of w with respect to x by partial derivative of x with respect to v. So that represents the relationship on the left side, on the left path here. And then on the right side, we want to go partial derivative of w with respect to y times the partial derivative of y with respect to v. So you multiply along each path going from w to v, and then you just sum over all the different paths. So I would point out here that all the derivatives that we've written down in this line of calculation, they're all partial derivatives. And the reason was that at both levels, we had multiple variables coming into play. So on this second level here, we had variables x and y, and on the bottom level, we had variables u and v. So that means that we talk about the partial derivative of w with respect to v, because w ultimately depends on two variables, u and v. We had partial derivatives here, because in that second level, w was a function of both x and y, and then we had partial derivatives on those two expressions there because the x and the y in turn depend on a couple of different variables, u and v. So we're going to do a few different examples, roll through a few different scenarios, and we'll see that sometimes it's regular derivatives you're writing down, sometimes it's partial derivatives. So the multivariable chain rule is not actually a formula, it's a process. It's a process of figuring out derivatives or partial derivatives from a diagram. And so we'll just do a variety of examples, maybe 2 or 3 more examples to get a feel for how this process works. Let's try another example. So here's a new situation, fresh diagram for us to look at. So w depends on x, y, and z, and each of x, y, and z are functions of t. So what we'd like to find here is dw by dt. So notice this is just a regular derivative. It's not a partial derivative. And the reason is that w ultimately just depends on the variable t. There's only a single variable at this bottom level. So by the time you express x, y, and z in terms of t, and then you express w in terms of x, y, and z, w would be fully given in terms of t. So let's try a similar strategy as we did in our previous example. So we're going to look at all the paths in the diagram from w to t. So there are actually 3 different paths. You could go through x, y, or z, and so that means there are going to be 3 different terms in this expression. Okay, so let's look at the first path. First path, we should write partial derivative of w with respect to x times dx by dt. Okay, now let's talk about this in a little bit more detail, because the first factor here, that's actually a partial derivative, whereas the second one is just a regular single variable derivative. So let's really understand the difference between those 2 factors. So the reason that we use a partial derivative for w is that when we think about traveling along this part of the path, see, at this level, w depends on multiple variables. So we need to say partial derivative of w with respect to x because w depends on several variables. However, when we do this part of the path, x depends on only the variable t, so that makes it a regular derivative. So when you are looking at each part of the path, you're looking at, as we travel from this level to that level, how many variables appear in this next level. If it's more than 1, then you use a partial derivative. If it's just 1, then you use a regular derivative from single variable calculus. Okay, so let's fill in our other 2 terms. We now need to talk about the path that goes through y. So we'd have partial derivative of w with respect to y times dy by dt. So that's a partial derivative times a derivative. And then finally plus partial derivative of w with respect to z times the regular derivative dz by dt. This last example illustrates a subtlety that can come up when we're doing these diagrams. I would say this is really the only subtlety that can come up. So we'll figure out what's happening here. So our variable w depends on u, v, and x. And then the variables u and v in turn depend on both x and y. And we want to find the partial derivative of w with respect to x. So the caution here is that the variable x appears in multiple levels. You can see x comes up in the bottom level, but also in the second level as well. And when that happens, it's best to be a little bit more specific about what's happening as we move from the top level to the second level. So we should actually say something like w is a function of u, v, and x. So we're just saying here, that's just a fancy way of saying w depends on u, v, and x. But the idea is that we're actually giving a name to how the variable w depends on u, v, and x. So we're going to call that f. And I'm just going to draw the f there beside the diagram in moving between the first and second level. And we'll see really why this matters when we write down our partial derivative. Okay, so let's try our usual thing of writing out our partial derivative, and we'll see what goes wrong here if we just follow our previous procedure. So we want to find the partial derivative of w with respect to x, and that means we need to look at all the paths that go from w to x in the diagram. So there's one that goes through u, there's another one that goes through v, and then there's a third shorter one where w just goes directly to x. Okay, so if we start mapping out these paths, we're certainly going to have 3 terms in this expression. Let's space them out a little bit better. Okay, and in that third path, I think initially, if we had not thought about naming the function f, initially we would just write something like partial derivative of w with respect to x. Okay, and this is going to cause problems because see on the left how we've got partial derivative of w with respect to x. So this cannot be equal to itself plus some other stuff. The problem is that we're using the symbol partial derivative of w with respect to x in two different ways. And that in general is a very bad thing to do. So the proper thing to do here is to take this term on the right, and instead of calling it partial derivative of w with respect to x, we should actually call it partial derivative of f with respect to x. So rather than talking about the variable w, we're talking about the function that defines the variable w. Okay, and by doing that, that's going to remove this issue of using the symbol partial derivative of w with respect to x in two different ways. So the idea behind the notation is that this thing on the left captures the entire expression of the rate of change of w with respect to the variable x, and we're saying that entire rate of change is a contribution of three different things. So in the first path, for example, we want to say something like partial derivative of f with respect to u, and then times the partial derivative of u with respect to x. So everything's fine in moving from the second to the third level. There's no need to do this business of naming the function. It's just in the first level, because x appears in multiple levels, that we have to be a little bit careful. So instead of saying partial of w with respect to u, partial of w with respect to v, etc., we're actually going to say partial of f with respect to u, partial of f with respect to v. And that way we're really clear that we're just talking about the partial derivative that's coming up from the first part of the path. There's no confusion between the different levels. Okay, so our middle term then is going to look like partial of f with respect to v. So that's representing the change, the rate of change that we're seeing visually in the first part of that path, and then we need to multiply that by partial derivative of v with respect to x. Okay, and then as we discussed, that third term, just coming from that single arrow there that we're seeing on the right side, much safer to call that partial of f with respect to x. So all these derivatives that we see in this expression are partial derivatives because each of our variables depends on multiple other variables. And remember that we only need to do this business of renaming our variable or reimagining it as a function when you have one of your variables appearing in multiple levels. So I would say that's sort of an exceptional case. Okay, from there, we're ready to jump into a numerical example.